Pascal's principle. This is an important principle. Very, very simple. Any pressure change that you create throughout a fluid, and remember, in a fluid, if you're deeper, the fluid pressure is higher. If you're shallow, the fluid pressure is lower. But any change in pressure, okay, will be transmitted throughout the fluid undiminished, which means if I add 2 pascals of pressure to the top of the fluid, the bottom of the fluid, which is higher anyway, will receive an additional 2. So that's this equation right here. What I do to one part of the fluid, I change the other part of the fluid. Now, this is very convenient because it's a basic principle behind hydraulics. It means that if I increase the pressure using a small pump at one end of a hydraulic system, okay, I will experience the same pressure change at the other end. But here's the key. If you remember, pressure is equal to force divided by area. That means that force, therefore, is pressure times area. So I can exert less force here, F1, if my area is smaller, A1, and get more force here with a larger cylinder piston, okay? So this means that any hydraulic system is just like a simple machine. You put work in at one end, you get work in out at the other end, but you can get more force at one end than the other as long as you conserve energy. Okay, so car lift is a great example of this. All right, in this particular case, I'm going to say what force must be compressed, air on the small piston in order to lift the car of 13,300 newtons. Okay, well, we just say what I do to one side, I do to the other side. Okay, pressure is force times area. Both cylinders are circular. The pi's and the r's, sorry, the pi's will cancel out on both sides. We're left with this expression right here, which compares the force and radius of each cylinder on each side. Okay, what's my new force going to be? Well, the small cylinder is 5 centimeters in radius. The large cylinder is 15 centimeters in radius. So I square both sides, multiply by the force that I need to exert. The car is going to be 13,300 newtons. I see I only have to apply 1,480 newtons on this side. So lift up 13,300 newtons on the other side. What air pressure would produce a force of that magnitude? Yeah, just plug in the numbers. Again, pressure is force divided by area. Here is the force, okay? Here's the size of the cylinder. May have mixed up F1 and F2, by the way. Sorry about that. And then you see, here's the force. There's the pressure. So not a whole lot of pressure. About 88% above atmospheric pressure. Show that the work done by the input and output are the same. That's just showing that, again, you've got to move this cylinder further to move the same amount or volume of fluid to get the car to move that much, okay? Now, here's a hydraulic jack. These cylinder jacks are very, very helpful. I use them on all kinds of equipment. I use them on cars. They can generate a tremendous amount of force for just a small amount of force on this handle right here, okay? Again, the principle is just Pascal's principle. You use a very small bore cylinder right here to force hydraulic fluid into the larger cylinder. And the larger cylinder is going to not move as far as the handle, but it's going to be able to exert a much larger force. It's also the principle behind brakes. When you step on the brake pedal, now we have power brakes. So there's actually some assist to this. It's not so much, master cylinder is actually getting some extra force. You press on that, you force brake fluid from the master cylinder into the calipers, which will close on the disc brakes and exert a force. And here you can see a schematic of that. This is neat because actually the foot is only exerting 100 newtons of force. However, due to the fact that it's a lever system, you exert many times greater force. As a result, this generates a large amount of pressure from the master cylinder, and this force is even further amplified by the larger cylinders in the brakes themselves.